Today we're going to be talking about some of the speech perception sort of problems or mysteries that I started outlining the other day. And we'll talk a little bit about this motor theory, excuse me, that the Lieberman and Mattingly paper is discussing. And we'll talk about some of the properties of that theory. And then next week, we'll start comparing and contrasting how motor theory approaches these perceptual mysteries in comparison to how other theories do so. So if you remember from earlier this week, we talked about the speech chain, where on this side you're going to have a speaker and various important things happen over here, but we're really mainly focused on this side, the listener, where you're getting from sound waves, that is pressure fluctuations out in the atmosphere, through the ear and into the brain. Although I would say for the kinds of stuff that we're talking about, it would be nicer to have maybe a mind here, because we're not right now trying to figure out exactly how all this stuff is represented in the brain, but we are interested in how people recover a linguistic message from that sound signal, which is really more of a cognitive or mental kind of domain than a neural one, but it's hard to draw a picture of a mind, so we have a brain there instead. Another way of putting this, here's the sort of naive model that we might have started with in speech perception. We're going to start with acoustic phenomena. So again, those pressure fluctuations out in the air, and we need to somehow end up with linguistic representations inside our mind brains. So phonemes, features, words, whatever you're eventually recovering from that signal. Here's like a totally naive, straightforward way of trying to do this. Humans, in the course of learning a language, learn how to map acoustic features or phenomena as sensed by the ear to specific linguistic features or specific speech sounds or whatever, right? Things like, this is a stop, that's a vowel, this sounds voiced, that one's coronal, so on and so forth. Right? As you're listening to a string of sounds, that is like a word or a sentence or whatever, what are you going to do? You're going to look for the acoustic cues to some particular feature, see if you find them, identify that feature, proceed to the next feature, and then when you've got all the features for that sound, move on to the next sound. At the end, what we'll have is a record of all the features in the order in which they came in, so to speak, and voila, there you have it, speech perception. So let me give you a kind of toy example of how that kind of a theory might work. Can you see this okay? Yeah, it looks like that's in the center of the screen. Okay, this is just a recording of me saying the English word cat. Cat. Sorry, that might be kind of loud. I should have warned you. And yeah, there's three segments in this word. There's a voiceless velar stop, k. There's a low front unrounded lax vowel, a. And there's a voiceless coronal stop, t. Right? So, what is our naive feature detecting model going to do? It's going to get some input into the ear that's going to look probably more like the spectrogram on the bottom than it does like the actual speech wave on the top. Well, this is physically what comes into the ear, the fluctuations in pressure over time. As I mentioned earlier, we talked about the human ear. Your auditory nerve really sort of separates the energy in this speech stream into its component frequencies over time. So maybe your input is going to look a little bit more like a spectrogram than it does like a speech wave. Whatever though, assume it's some kind of a representation that you're able to recover features from. And first we're going to hear something like this. And what are we getting here? Well, is this sound plus voice or minus voice? It's minus voice, and we know that because there's no periodic component down here, real low frequency range. Is it a vowel? No. Is it a sonorant consonant? No. Is it a stop? Well, there's this very sharp burst in energy right here. So yes, this must be minus continuant, minus voice, minus sonorant. It's a stop. It's a voiceless stop. It's also got this aspiration period over here. Here's what that sounds like. So maybe that's represented in English phonology, or maybe it isn't. Maybe it's predictable, whatever. So we've got those features. We move on. We get something like this. Right? What are we going to do with that? Well, clearly has some low frequency energy here and a periodic wave, so it's going to be plus voice. There's a number of higher frequency components in this sound. So here's a formant, here's a formant, here's a formant, here's a formant. It's a very loud sound, so it's probably a vowel plus syllabic plus sonorant, so on and so forth, minus consonantal. What kind of a vowel is it? Well, it's got a formant here around 900 hertz, 800 hertz, so it's probably going to be minus high plus low, and it's got a second formant here around 1700 hertz, so depending on the speaker, maybe that's plus back or maybe it's minus back. It's going to be a little bit hard to tell. There's a third formant. There's even a fourth formant. We don't do much with that, but we're going to look at these features and we're going to figure out how to map them onto linguistic ones. And then eventually we're going to get this. And again, there's total silence during this part, so it's definitely voiceless and probably a stop. And then we're going to get this burst thing here, and maybe that's going to tell us whether it's coronal or velar. Although, note that this sounds very similar to this in isolation. Not so different. It's not really clear that you actually get that place of articulation information from the burst alone. But anyway, this is our naive model. So we all got that. That's like the naive version of how we're going to do speech perception. Features come in, you hear them, you perceive the speech, right? That's basically it. But, and here's where the interesting stuff comes in, there are some problems. Let me split this out in a separate video.